What is an electric field? That's bookwork. A region of space in which charged particles experience a force. The direction of that is the movement that a positive point charge would undergo. In other words, it's from positive to negative. Draw a diagram representing the electric field around these two small conducting spheres. Now, the first thing is that both of them have a bit of a spherical nature. Okay, so we're going to go like that. We're going to go like that. This one's 5 coulombs, so I'm going to make it a little bit more dense than the 3 nanocoulomb one. And then between the two there is a link, and it goes from positive towards negative. And there's this and this. So in between, you can't make the one side stronger than the other. Obviously, they're linked. But somehow I needed to see that the 3 nanocoulombs had less field lines around it than the 5 nanocoulombs. And we go away from the positive 5 and towards the negative 3. Along the line joining the two small spheres, there is a point P, which is 10 millimeters from the plus 3 nanocoulomb charge. Determine the resulting field strength at that point. So we are going to go 10 millimeters over here. Sorry, it's 10 over there, okay? And then obviously that means that there's 50 left over there. Now, it's a resulting field strength, so I need to work out the electric field due to the minus 3 and due to the plus 5. So let's see what we can do about that. The first thing is to say, what is the electric field strength as a result of just the minus 3 nanocoulombs? It's equal to K Q over R squared, which is equal to 9 times 10 to the 9 multiplied by 3 times 10 to the negative 9, and it is 0.01 squared, and I land up with 270,000 newtons per coulomb. And remember, it's from positive towards negative, so that is going to be to the left. The next one is to say, what is the electric field strength on account of the 5 nanocoulomb? Exactly the same formula, except this time it's 9 times 10 to the 9, 5 times 10 to the negative 9, divided by, and this time it's 50 millimeters, so it's 0.05 from the charge that I'm interested in, or that's causing an electric field, and I land up with just 18,000 newtons per coulomb. Again, it is going from positive to negative, so it's left. Now I need to work out a resultant, which means I add those together because they are both in the same direction, and land up with 288,000 newtons per coulomb to the left. State Newton's universal law of gravitation. So, any two objects in the universe attract one another with a force that is directly proportional to the product of their charges. This is Newton's universal law of gravitation. Sorry, directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. The next thing that we need to do is we've got to calculate the magnitude of the gravitational force acting on a man of 85 kilograms when he is a certain distance above the Earth's surface. So I need to add this 953 to the radius of the Earth and convert that into meters. So first I'm going to just go F is equal to G M1 M2 over R squared, 6,67 times 10 to the negative 11. The mass of the man was 85, and the mass of the Earth is 6 times 10 to the 24. Multiply those all together and then divide by 6371 plus 953. All of that times 10 to the 3, because I want to make it into meters, and then square it. And when I get an answer, it is 634,16 newtons. The man weighs 784 newtons on Earth. How much would he weigh on a planet with twice the mass of Earth and 3 times the radius of Earth? Remember that gravitational acceleration and therefore weight and therefore the force of attraction is all going to be mass of the planet r squared. So we can say that if I have twice the mass of the Earth, I need to double that value. So it's 784 times 2. And then 3 times the radius, that means I need to divide by 3 squared. So that would need to be 3 and it would have to be squared, so it's divide by 9, and I land up with 174,22 newtons. Consider the following list of molecules, and from the list select polar molecules. HCl is polar. Ammonia is polar. They've got an electronegativity difference. Your BF3, although they are polar bonds, it is a trigonal planar molecule, and it turns out to be somewhat nonpolar overall. So I would leave that alone unless they'd like to know what is a trigonal planar one. Use ones that you are very familiar with. HCl, definitely. Ammonia is definitely polar. Water is definitely polar. Nonpolar, definitely your methane, your carbon tetrachloride, your carbon dioxide. And quite frankly, this is methane. If I double it, it becomes C2H4, kind of like. That's also nonpolar. But if you know nothing about it, say nothing about it. You only have to get 2 of each one. So you need 2 of the polar molecules. You need 2 nonpolar molecules. One that is pyramidal in shape, your classic pyramidal, is going to be ammonia. One that is angular in shape, your classic angular, is water. And you should know these. One molecule that has a tetrahedral shape, well, you should know that your carbon tetrachloride and your methane are both tetrahedral in shape. Carbon dioxide is a gas that's toxic to humans. It is linear in shape, they tell us that, and a nonpolar molecule. That's interesting. Draw a Lewis diagram for the carbon. So I'm going to go oxygen, 1, 2, 3, 4, 5, 6. Another oxygen over here, 1, 2, 3, 4, 5, 6. The carbon brings 4. And then we are going to say that oxygen shares there, that oxygen shares there, and the carbon shares those 8 electrons over there. Calculate the electronegativity difference between carbon and oxygen. And what you find is that the carbon has got an electronegativity of 2,5 and oxygen of 3,5. Therefore, the electronegativity difference is going to be equal to 1. What does your answer in 6.2.2 suggest about the bonds between them? They are polar bonds, okay, because there's an electronegativity difference between them, with the oxygen being slightly negative and the carbon being slightly positive. That's what we learn from that particular piece of information. But then it goes on to ask us a little bit more. Is the CO2 molecule polar or nonpolar in nature? Well, just a little bit earlier, we got told it was nonpolar, so best we write nonpolar, and now we need to explain ourselves. The reason it is nonpolar is because it is symmetrical in shape, and the 2 polar bonds balance each other out, resulting in 0 electrostatic force between them. So you needed to maybe say linear, symmetrical, balanced, or balanced electrostatic forces. Consider the molecules of carbon dioxide and ammonia. Using your knowledge of molecular polarity, what type of intermolecular forces, we're not talking about the bonds anymore, we're now talking about the intermolecular forces. We know that carbon dioxide is nonpolar covalent, and therefore it's a nonpolar molecule. It will be held together by London forces. And the ammonia molecule is one of your classic hydrogen bond forces. Why? Because it's nitrogen with hydrogen, or oxygen with hydrogen, or fluorine with hydrogen. They are that exception hydrogen bond force. Which of these two compounds would you expect to have the highest boiling point? Give a reason for your answer. Well, obviously the one that has the stronger intermolecular force, so that is going to be ammonia. It has stronger intermolecular forces and therefore is more difficult to separate. So the diagram below shows the reaction between hydrogen gas and chlorine gas to form HCl. And what do they tell me about that? They've told me the bond energy of each of them, the activated complex, the bond making energy, and the questions are as follows. Is this reaction endothermic or exothermic? Give a reason for your answer. Since I'm going to release more energy than take in energy, it is an exothermic reaction. More energy out than in. What is the value of the enthalpy or the heat of this reaction? It's going to be equal to the 680 minus the 860, and I land up with 180 kilojoules. Represent the equation on a potential energy graph and fill in all of those details. So this is the graph that we're expecting. You need to know to label this reaction coordinate. And you need to know to label the y-axis EP, potential energy. If it's an exothermic graph, I need to have less energy in the products than in the reactants. Energy of products is at the end. The end is the product, and energy of reactants is what we start with. If I need to put in delta H, it's the difference between the energy of the products and the reactants, and that happened to be 180 kilojoules. I don't think you had to put the value on. The activation energy is from the energy of the reactants up to the activated complex. They didn't ask for you to label the activated complex in this case, but that is where the activated complex is, and that is your activation energy.